Hi, I wanted to do a series of videos in this last week of classes on some of the most asked about topics. So to start with, I'm going to do method of moments. Okay, so the motivation for method of moments is to estimate parameters like we do with MLE in a distribution with multiple unknown parameters. And we want to do it fairly easily. I did a series of videos on MLE, and we did, for example, the normal distribution with both parameters unknown. And I mean, it wasn't impossible, but it was fairly computationally heavy, so which say MLE can be very heavy to use with 2+ parameters. Like, we had to take 2+ partial derivatives plug them in, and just a lot, right? For some distributions, for example, the gamma distribution, you'd have a very, very hard time even finding the MLE. So that brings us to method of moments. Method of moments is usually less computationally difficult. But one caveat, I guess, for method of moments is that usually when we have the choice, what I mean by that is when, MLE isn't going to be impossible for us to do, isn't going to be significantly more work. MLE is the better choice. What I mean by that is it has a stronger theoretical background. And will typically be more efficient. But I think that's probably outside of the requirements for this course, because realistically you'll be told to find the MLE estimate or the MOM estimate. So then the question is, how do we use method of moments, right? So I guess the first question I would ask is, how many parameters are there? Right? Let's say that there's n. N being an arbitrary amount, obviously. Then we have a system of equations. We would do 1 over... I know I just said that there's n parameters. I'm going to change that to m. Because then we have 1 over n times sum of xi is equal to the theoretical first moment. Then 1 over n sum of xi squared is equal to theoretical second moment. And we can do that m times, because we have m parameters. We have 1 over n sum of xi to the mth power is equal to theoretical mth moment. Right? Now, from these, we have m equations, m unknowns, and we can solve for each parameter, or our estimate for each parameter, that is. I'm going to write theta hat sub 1 MOM to signify we used method of moments, theta hat sub 2 MOM to theta hat sub m MOM. Now, one note that I want to make before I close out this first video. We can use, and depending on how easy each one would be, we may use 1 over n sum of xi squared, for example, as the theoretical second moment, back when we were plugging that in into the system of equations. Or 1 over n sum of xi minus x bar squared, which would be the theoretical variance. Again, just use whichever one is easier, whichever one we happen to know more about. Generally, what I mean by that is if we have a distribution where we know that the theoretical variance is in a simpler form, we should use that. If the theoretical second moment, sum of xi squared, is in a simpler form, just use that. So really it's a judgment call. Both will get you the same answer